All right, everyone, welcome to class. Today is March 8th, 2021. So some announcements. So make sure you do your test 2 on Canvas. Okay, multiple choice should be up and running on Canvas. And make sure you upload the written problem set for test 2. All right, if I make any errors, I'll give the points back. And if there's any mistakes on the multiple choice, I'll give the points back. But for now, make sure you turn everything in by midnight tonight. Also turn in your quiz 2 by midnight tonight as well. Okay, so today I'm just going to go over chapter 15 material, new material. Just want to make sure that after class you do all these things at home or wherever you are, the dorms, wherever you may be. So that's the major announcement for today. So a little bit of work for you guys after lecture. If you have not done so already, make sure you turn in your exam online. And also do your lab report for rate of reaction. And that we'll make that due Friday. This Friday. And this Friday we will have a new lab, and I believe it's Le Chatelier's principle. So this Friday there's a new lab. So if you're Group A or Group B, or if you just want to come to the lab, we don't have Group A, Group B anymore. So this Friday is a new lab, Le Chatelier's principle. So make sure you come to lab and make sure you do your lab reports. Principle, P-A-L? P-L-E? Right, so that's the situation with regards to the labs. And, continue doing clutch prep. I see one of our students, Robert, has his clutch prep notes out. So looks like it's a big help for some of the topics here, which are a little bit more difficult. I also saw Robert last night. So make sure you do your clutch prep drills. All right, I appreciate him doing that, and I appreciated him coming to my office hours last night. And I believe, Elena, I think you're on top of things. Is Wednesday a holiday, dear?
Mm-hmm.
Okay, Wednesday is rest day. All right, so do not come to class Wednesday. Okay, since there's no spring break, you have a rest day Wednesday. If you need me, you can schedule a Zoom meeting. I'll probably take that as a rest day too. But you can you can email me or set up office hours or set up a meeting with me on Wednesday if you so desire. All right. First thing I would do is definitely get that test and quiz and problem set up in Canvas. And lab this Friday. Do the online thing if you paid money, the $30. Anything else? Joshua, can you think of anything?
Homework 14 is done tonight too.
Homework 14. Okay, turn that in. I'll put the 10 points in. Homework 14 is due. Probably was due last Friday, I think. I do want to say thank you. Thank you, Elena, and I'll start homework 15 if you get a chance. I think I recorded all the videos for that, so you can use that to help you. All right, so yeah, tough stuff here, so you guys should be proud of yourself managing this and all your other classes. So a lot going on in your busy lives. All right, chapter 15 here is talking about acids and bases. So let me just start off with a little bit of a teaser, okay, an appetizer for acids and bases. So how many of you have heard of pH? Okay, how many of you have heard of acids and bases? Okay, so let's talk about it in terms of chemistry. Okay, acids and bases in terms of chemistry. First off, an acid, okay, we're talking about what is known as Brunstad acids and Brunstad bases. Okay, Okay, so that's what we're talking about. There's also something called Lewis acids and Lewis bases. Okay, not talking about that. And in this context, Brunstad acids will generate what I'm going to call a proton, or H+. Now it's very important not to get confused on this, everyone, that H+ and H3O+ are the same thing. So the way I'm going to teach this, H+ and H3O+ are exactly the same. And Brunstad bases are going to generate the opposite of H+, and the opposite of H+ is OH-. Okay, we call this the hydroxide ion. Another thing I want to tell you is not only do Brunstad acids generate H+, another definition I'd like for you guys to know is that they give away this proton. They give away a proton. Okay, some acids can give away more than one proton. Okay, so I'll just say give away H+ protons. Okay, you can give away one proton, 2 protons, 3 protons. As an example, I have H2SO4. This is called sulfuric acid. How many protons do you think sulfuric acid could give? How many? 2. Okay, 2. Okay, so we call that a diprotic acid. Okay. Anybody here an avid Coke drinker? Nobody drinks Coke. Everyone here is healthy. Okay, this is called phosphoric acid. I can tell you Coke has a lot of phosphoric acid. It's like a drug, this Coke. It's a phosphoric, Coke has phosphoric acid besides many other things. How many protons do you think phosphoric acid can give? Okay, not 1, not 2, but 3. So we can call phosphoric acid a triprotic acid. So just realize that some acids can give away more than one. All right, the standard acid, how about HCl? We call this hydrochloric acid. Okay, how many protons can it give? 1. So we call this monoprotic acid. So just keep in the back of your mind that some acids can be diprotic. Okay, some acids can be triprotic. And then some acids, in our study of acids, are going to be monoprotic, giving away 1, 2, or 3 of this very important, I guess you'll call this molecule, known as H+, which is the same thing as H3O+. Okay, same thing. The way I'm teaching it, it's the same thing. And finally, I want to tell you guys is that bases not only generate hydroxide ion OH-, but you see, if you give away a proton, someone needs to take the proton, so these will take the proton or abstract. Let me use a fancier term. The term I'll use is abstract. Okay, they will abstract H+ or protons. Okay, they will abstract protons. So for every giver, there's a taker. Okay, for every giver, there's a taker. All right, so that is our preliminary definition of what a Brunstad acid is. Okay, not Lewis acid, totally different. And a Brunstad base, again, not a Lewis base. Again, that's totally different topic. Okay, one gives away protons. For every giver, there's a taker, and the taker will be the base, Brunstad base. So 2 things about acids: they generate H+, they give away H+. Bases generate OH-, and they take the proton. They take the proton. All right. I would like for you guys to memorize these 6, what I'm going to call strong acids. Okay, you see some acids are just very good at delivering protons. Okay, some acids are just very good at delivering protons. See, if I'm an acid and Connor is an acid, who's better at generating H plus? Who's better at giving away H plus? Who's better, either me or Connor? Well, we have a list. We have a list of all the hundreds of acids that are out there. Some acids are just better than others. Well, I want you guys to know that of all the hundreds or however many acids they are in the world, there are 6 of them that are considered strong. 6 strong acids. Okay. So one of them is HCl. Okay. Let me write the equation for HCl. Okay. Acids give away H plus, and here they're going to give it to water, giving you H3O plus Cl minus. Okay, so that's a strong acid. Okay, so that's strong acid number 1. Okay, this is called hydrochloric acid. Okay. Strong acid number 2 is H2SO4. Let me give you the acid equation. Here it's going to give it the H plus to water, giving you H3O plus and HSO4 minus. Okay, this is called hydrochloric acid. Okay, this is called sulfuric acid, excuse me. Strong acids, you want to memorize those. Okay, the third strong acid on our list is nitric acid, HNO3. Okay, acids do what they're going to do. They're going to give away that H plus. It just so happens that these 6 of them do it so exceedingly well. It's going to deliver that H plus, giving us H3O plus NO3 minus. Okay, this is nitric acid. We have 4, 5, and 6 left. Okay, strong acid number 4 is this one that you may have seen in your flashcards, HClO4 plus H2O. Acids do what acids are going to do, give away that H plus. This is called perchloric acid. Okay, we have 5 and 6. Strong acid number 5 is going to be HBr, hydrobromic acid. Acids do what acids are going to do, give away that H plus. Okay, this is hydrobromic acid. Hydrobromic acid. Okay, and our final strong acid here, we just want to memorize this, is hydroiodic acid, HI, plus H2O. Hydroiodic acid. Okay. These are 6 strong acids. Okay. So let me expand on this term strong acids. Okay. One, I think you just have to bite the bullet and memorize these as strong acids. Okay. All right. So what makes them strong acids? Okay, look at the arrow. Okay, I'll highlight this in pink. Look at the arrow. The arrow is one direction or two directions? One. Okay, these are like 100% completion. Okay, remember in our discussion of equilibrium in our last chapter, okay, an equilibrium reaction, here's our products P, here's our reactants R, they kind of settle. A little bit of reactants, more products, a little bit of products, more reactants, whatever. Okay, it's these 6 strong acids, it's not like this. It's like, okay, it's all products. Okay, or at least 99% products. They're all products. That's why we put this here as the arrow in one direction. Okay. So we say they go to, not everything is 100%, not everything is perfect, but we say that this reaction is very much close to 100% source of protons. Close to, okay, 100%. Ionization. 100% ionization, 100% source of protons. It's just these 6, okay? It's just these 6. Look at the arrows and realize it's 100% source of H3O+. Okay? One more thing I want to tell you guys here is, you see this HCl, obviously it's the acid. Oh no, okay. Okay. What does H2O liquid serve as? This is H2O liquid, obviously. This is the solvent. What would H2O be in this situation? If HCl is the acid, what is H2O? It's the base. You see, it's taking that. It's abstracting or taking that proton. Okay, I'll call that a base. Okay. And this acid, I have to watch this because I notice this is confusing to a lot of students. This acid delivers that H+. When it delivers that H+, what does it become? It becomes Cl-. We're going to call that the conjugate base. Okay. H2O picked up that H+, and when it picked up that H+, what did it become? It become this acid, hydromonium acid. We're going to call this the conjugate acid. Okay, let me put the pairs. So this is like a couple. Okay, they're a couple. Okay, this is, I'll box it in green. This water is the base. And to that base, we have its conjugate acid. They're a couple. Okay, they're a couple. Can we identify the acid conjugate base pair here? Okay, obviously sulfuric acid is the acid. Okay, what is its conjugate? HSO4 minus, which I guess this is called hydrogen sulfate ion. I don't know the exact terminal nomenclature, but yes, that is its conjugate base. Okay, what is water here? What is water in all of these? Water is the base, and what is its conjugate? Is H3O+, okay, the conjugate acid. Okay, everyone see that? And like that, we can do it for this, 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 and this. Okay, so when we do our acid-base reactions, we have to know that there's going to be a conjugate. Okay, the acid delivers the proton. The The acid delivers the proton and it becomes its conjugate base. The base takes that proton, the base abstracts that proton, and it gets converted to its conjugate acid. Okay. All right, so we need to memorize these 6 strong acids. Once again, hydrochloric acid, sulfuric acid, nitric acid, perchloric acid, HBr hydrobromic acid, and hydroiodic acid, HI. Memorize these 6. Okay, what will be all the other acids? All the other acids will be weak. Okay, what do we do with weak acids? Okay, well, first of all, if it's a weak acid, will the arrow be one direction? No. Okay, for all the other acids that are considered weak acids, unfortunately, we will have to use, the arrow is like this, back and forth, weak acids. And unfortunately, because if they're not a strong acid, they're a weak acid, the arrow's back and forth. What I was trying to say is that we will have to use the ice table. Ice table, okay, to do our problems. Okay, so 2 things with weak acids. Also the same thing with weak bases. Okay. And our problems, first of all, the arrow is going to be back and forth, so it's an equilibrium, and we will have to use an ice table, because they're weak. Okay? They're weak. They're not 100% moving to the product side. So just letting you guys know, if it's not one of these 6, you've got to have to use an ice table for those acids. If it's not a strong base and it's a weak base, you're going to have to use the arrows back and forth and use an ice table. So what are some strong bases? Anything that has an OH in it. Okay, so strong bases are going to be group 1 and group 2 hydroxides. Okay, so the classic example is going to be NaOH, okay, which is really just Na plus and OH minus. Lithium hydroxide, these are ionic compounds. Very, very good source of OH minus. These are your typical, stereotypical strong bases. Okay. Sometimes barium hydroxide. It gets a kind of tricky here for group 2, but calcium hydroxide. So I'll just put a little asterisk by here. But they're group 1 and group 2 metals. So this is also a source of OH minus. A very good source of OH minus. Okay, remember, all of this is happening in water. Okay, all your acid-base chemistries, all the reactions in your body, in your cell, they are happening in the solvent of water. So, I'm not being explicit here, but all of these reactions are happening dissolved in water, aqueous. AQ is the state. The reason why I put asterisks here is because it's a little tricky. We have not studied this, but sometimes these like to precipitate. Okay, remember our solubility table way back in chemistry 1? So these may precipitate. That's the only reason I put an asterisk by it, because sometimes they may form a white solid, not totally liquid. Okay, not totally a solution. but they're still strong bases as long as you can get them dissolved in water. Okay? As long as you can get them dissolved in water, it's a source of OH minus. Okay? All right, so these are your strong bases. Okay, look for the OH anywhere in the molecule. Okay, these are ionic compounds. Look for the OH. So strong bases, look for the OH. Let me tell you what a weak base is, and this is something like your 6 strong acids you will probably have to memorize. But this is a classic example of a weak base, just as these are classic examples of strong acids. The classic example of a weak base is NH3. NH3 is called ammonia. That's the name of that molecule. So this is a weak source of OH minus. Okay? So let me give you that equation here. We have NH3. All of this is happening in water, plus H2O. Okay, NH3 is a base. Okay, what do bases do? Will bases give away protons? Or will bases abstract and take protons? Take. Okay, who's going to take it? Ammonia. Who's going to give it? Water. See, water is really an amazing substance because it could do both. Okay, here, let's go back to our first page of notes. Here I have water taking that proton. You see? Well, ammonia, I have water giving that proton because ammonia is a base. It's a weak base. It's not going to do it 100%, but it's going to do it. It's going to take it very weakly. It's going to take it from water. Because it's a weak base, notice my arrow here. It's not one way, but 2 ways. And NH3 takes that proton, it becomes the conjugate, NH4 plus, this is happening in water. The H2O gives away that proton and it becomes OH minus. Classic example of a weak base. Okay? So here is our ammonia, NH3. This is, as we stated before, it's a base. It's a weak base. If this is the base, this has to be the acid, water. Okay, the base ammonia takes that H+, and when it does, it gives you the conjugate acid, which is called ammonium ion. You see, this is ammonia. This is called the ammonium ion. Water, being the acid, delivers that H+. And as it delivers that H+, it becomes its conjugate base, which is OH minus. So amazingly, NH3 is a source of OH minus. Do you see that? NH3 is a source of OH minus. Okay? Thanks to the help of water. NH3 is a weak source of OH minus. All right, anytime we have the equilibrium, we have an equilibrium constant. Here I'm going to call it Kb. So Kb here is going to equal to products over reactants, NH4 plus concentration times OH minus concentration divided by concentration of NH3. Okay, everyone see that? Okay, products over reactants. Why did I not add H2O? Be- because it's a liquid, no solids and no liquids. Okay. So this is your standard definition of Kb, specific for ammonia. Okay. And let me go back here. These are strong acids, right? Okay. Will these have a Ka? The answer is yes, they'll have a Ka. What do you think their Ka will be? Will it be very high or very low? If you have $1 million, are you moving this way, forward in life, or backward in life? Forward. Okay, these are moving forward, 100% forward. So their Kas are very, very large. In fact, I think in your notes I have the Ka values in a table. Very large. Very, very large. Okay. These are moving forward in terms of their reaction. Okay, $1 million reaction. Not million, billion. If you have $1 billion, are you moving forward in life? This is like $1 billion because they are very large. Okay. And when I say very large, much, much greater than 1. All these Kas, A stands for acid, all these Kas are very large, okay, implying that the reaction is moving almost 100% in the product direction. Okay. Now, the minute you get to the weak bases, okay, they are not going to 100%. The strong bases, they're going to move to 100% OH. Okay, strong bases 100% source of OH minus, close to 100%. Strong acids close to 100% source of H plus. Your weak bases, not really. Okay, very poor source of OH minus. All right, let me give you a classic example of a weak acid. So there's tons of weak bases that you will have to familiarize ourselves with. There's tons of weak acids that we will have to familiarize ourselves with. Well, let me give you a classic example of a weak acid, and this is called acetic acid. This is called acetic acid. So let's write out the equation for this. Okay, acetic acid is CH3 COOH. Okay, this is all happening in water. So anybody eat a lot of salads and put vinegar in their salads? So vinegar has a lot of acetic acid. You're actually having acetic acid in your body when you have vinegar, usually used a lot in salad dressing. I also think it's nail polish remover, if I'm not mistaken. Okay, so acetic acid plus water. Okay, this is called acetic acid. Again, it's a classic example of a weak acid. It's not one of our 6. It's not one of our 6, so we're going to use the back and forth arrow. Okay, what will acids do? Okay, they'll give away that H plus. Okay, and in doing so, this acetic acid becomes the conjugate. The conjugate is this structure. Okay, okay, and that's called the acetate ion. Acetate. This is all happening in water. H2O takes that proton, it becomes H3O plus. Okay. So acetic acid is a source of protons. Acetic acid is a source of protons. Is it 100% source of protons? No, it's a weak acid. Okay, so like that, this will have a Ka. All right, let's go ahead and write this Ka. The A stands for acid. Products over reactants. So it's going to be H3O plus times acetate is CH3COO minus divided by CH3COOH. Concentrations. Why did I not add water? Because it's a liquid. Liquids do not go into this thing. Right, one final thing here. Acetic acid obviously is the acid, hence the name acetic acid. Okay, it delivers that proton. It becomes the acetate ion. We'll call that its conjugate base. And then water takes the proton. You see that in green. And water taking that proton makes it the base. Let's circle this. When it takes that proton, it becomes H3O plus. We call that the conjugate acid. So here is our pairs. Okay, in green, conjugate base acid pair, conjugate acid base pair. Okay, that's an example of a weak acid. Right? We can look up the Ka in the book. We can look up the Kb in this book. Okay. Actually, let's look up this Ka here. The Ka for this is 1.75 times 10 to the minus 5. Okay, so this is something you will have to look up in a book. So this Ka is 1.75 times 10 to the minus 5. We quote it at a specific temperature, and here it's at 25 degrees C. So it's a source of H+, but not a powerful source of H+. And then Kb here, this is in page 2 of our notes. Kb here is 5.62. Wow, 5.62 times 10 to the minus 10. Wow, that's a very, very weak source of OH minus. Why? 10 to the minus 10. Very, very small number. And this is at 25 degrees C. Okay, we quote our equilibrium constant at a specific temperature. All right, so a lot of times people don't like exponents. Okay, how many of you like exponents? You don't like exponents? A lot of people don't like exponents. So instead of saying Kb, people will like to use the term pKb. Okay, instead of using the word, the concentration of H+ is yada yada yada, people like to use the word pH. The concentration of OH minus is blah blah blah. People would like to use POH. Instead of saying fancy exponents, you can actually make the numbers a little bit more digestible. Other than that, that's the only thing between pH and H3O plus or H+. That's the only difference between OH minus concentration and POH. The only difference between Kb and pKb is to make the number whatever. You don't avoid writing these messy exponents. So the P here stands for power. Okay, power. So pH is the power of H. We live in a pH world, but we can easily live in a POH world. Power of Kb, power of OH, power of H+. It's the minus the log of the value. So pKb is minus the log of your Kb value. Okay. I can do a P Harper. Okay, if pKb is minus the log of Kb, pKa is minus the log of Ka. Okay, it's just minus the log of something. pH, now we should know, is minus the log of H plus concentration. pOH is what? Minus the log of the OH minus concentration. It's minus the log. Anytime you see that power P, lowercase p, it's minus the log. So using that same rule, P Harper is just minus the log of Harper, whatever that means. Okay? Whatever that means. You can have P boat or P chair. Okay, what is P chair? Minus the log of chair. Okay, again, meaningless, but that's what power means. Okay, minus the log. So PKB is minus the log of KB. Let's take the PKB of this value in our calculator. So minus the log of 5.62 times 10 to the minus 10. That will give us PKB, also known as power KB. And doing this in our calculator, let's see, how can I do this here? Log 5.62 times 10 to the minus 10. Okay, that's log, but it's minus the log, so minus the log gives me 9.25. Okay. So I have to try to convince you that this value of 5.62 times 10 to the minus 10 and 9.25 pKb mean the same thing, okay? It's just, instead of saying, hey, 5.62 times 10 to the minus 10, people will say 9.25, okay? Let's do the pKa for acetic acid. Okay, minus the log of our Ka. So let's do that. It's going to be, let's do it straight up. Minus the log of, this is the value I got from the textbook, 1.75 times 10 to the minus 5. Close those parentheses. 4.76. Okay. So I have to convince you that 4.76 pKa means the same thing as 1.75 times 10 to the minus 5 Ka. Okay? It's just that we are not saying, instead of saying 1.75 times 10 to the minus 5, the power of this acid is basically 4.76. That's called pKa, pKb, and then there is pH, and then pOH. Again, P stands for power, and it's the minus the log of whatever. Okay, minus the log of whatever. All right, let's go back to our notes here. Okay, something really amazing happens. Well, let's just rewrite this again. Let's see how much I can finish this in our last 5 minutes or so of class. See, this is something I want you guys to memorize, not just the 6 strong acids, but the generic equation. This is generic, okay? For any weak acid, it's going to be like this. Okay, don't forget your back and forth arrows. Okay, this is going to be Ka. We can do the same thing for Kb. This is the generic, keyword generic Kb equation. Okay, again, look at my arrows. This is the generic Kb equation. Okay. Once again, here is our acid conjugate base pair. Here is our base conjugate acid pair. Right? We're going to add these two reactions together. And it's very, very amazing what happens when you add these two reactions together. Okay, when you add these two reactions together, this A minus cancels out with that A minus, and that HA cancels out with that HA. So we're left with 2H2O is at an equilibrium with H3O plus OH minus. Now when you add two reactions together, if you took the exam already, you'll realize that you have to multiply the equilibrium constants. So this equilibrium constant is Ka times Kb. We're going to give it another name, Kw. Kw at 25 degrees, we can look this up in a textbook. Kw for this equilibrium reaction at 25 degrees is 1.00 times 10 to the minus 14. Okay, remember, these equilibrium constants are unitless. So that's the equilibrium constant for water. Okay, what is Kw? Okay, it's an equilibrium, so products over reactants. Products, H3O plus, product OH minus, divided by reactants. Okay, why am I not adding any reactants here? Why am I not adding any reactants? Because it's a liquid, right? It's a liquid. All right, so here's our first equation that we can derive, Kw. Right. What I'm going to do now is I'm going to take the natural log minus the natural log of both sides of the equation. You don't have to do all this derivation, but we're going to take the natural log of both sides of the equation. So this means I will take the minus the log of Kw equals minus the log of H3O plus times OH minus. You're allowed to do that. You're allowed to take minus the log as long as you do it to both sides of the equation. Anybody know this math rule? Okay, this is not a math class, so I don't expect you to know it, but log AB is equal to log of A plus log of B. Okay, so that's just an algebra rule, not necessary for this class. So I'm going to use log AB equals log A plus log B for this. Okay, so that's going to make it minus the log of H3O plus. Okay, plus log B, but you see that minus sign there? Okay, so I'll just do it. Plus log AB is going to be log A plus log B, so it's going to be log A H3O plus log B, but I'll put the minus sign here. So that becomes minus and this still stays as minus log Kw. So let me rewrite that step here. Okay, so here this becomes minus log H3O plus log OH minus. Okay, but I'm distributing out the minus sign. Okay, there's no derivation on the exam, so minus log Kw is equal to minus the log of, I'll just call that H plus, minus the log of OH minus. All right, the final minute here. Okay, we know Kw is 1 times 10 to the minus 14. Equals minus log of H plus. What is that? Minus log of Harper is P Harper. What's minus log of H plus? PH. Plus What's minus log of OH minus? Very good, POH. What is minus the log of 1 times 10 to the minus 14 in our calculator? All right, minus, that's KW, which we looked up in our book, minus the log of 1.00 times 10 to the minus 14. 14. Oh, that's a mic drop, or calculator drop. And this is the equation that we should know. Okay. All right, so we derived 2 equations here. One is the KW, and this is our second equation here. All right. So we will continue with this on Friday. So make sure you do your exams. If there's any issues, please email me. Have a good day. Yes, Wednesday is rest day. You do not need to know all this derivation, just need to know this and this.